When a massive star dies, it explodes with unimaginable force, a supernova. But from that violent death, a tiny ultra-dense remnant is born, the neutron star. How does such a dramatic transformation unfold? Stay with us as we reveal the science behind it. If you enjoy this journey, please like, subscribe and share, and tell us in the comments what fascinates you most about neutron stars. Thank you for watching. Now let's begin. A massive star evolves through a long chain of nuclear burning stages. At the beginning of its life, it shines by fusing hydrogen into helium in its core. This process continues steadily for millions of years and generates the radiation pressure that balances gravity. When the hydrogen in the center is exhausted, the core contracts, heating until helium fusion ignites. Helium nuclei combine to make carbon and oxygen. Later, the core continues contracting and new shells of fusion appear. Carbon burns into neon, magnesium and sodium. Oxygen burns into silicon and sulfur. Finally, silicon nuclei fuse to produce iron and nickel. Each stage occurs at higher temperatures and pressures than the last, and each stage is shorter in duration. Hydrogen fusion lasts millions of years. Helium fusion lasts hundreds of thousands of years. Carbon burning endures for centuries, oxygen burning for only a few years, and silicon burning for mere days. By this time, the star is swollen to enormous size. Its radius may reach hundreds of times the distance from Earth to the Sun. At the surface, it glows red and cool, appearing as a red supergiant, but in the interior, the temperatures rise to billions of degrees. The structure resembles concentric shells, each one a site of fusion for a particular element surrounding an inert core of iron. The layering is stable for only a short while because iron does not release energy when fused. Unlike lighter elements, iron nuclei are already tightly bound. If fused, they absorb rather than release energy. If split, they also absorb energy. The star therefore cannot extract pressure support from iron fusion. As silicon burning finishes, iron accumulates at the center. The mass of this core grows steadily as the fusion shell continues to feed it. The only force resisting gravity in the core is electron degeneracy pressure. This pressure comes from the Pauli exclusion principle, which states that two electrons cannot occupy the same quantum state. When electrons are squeezed together into extremely dense matter, they exert an outward push, even at absolute zero temperature. This is the principle that stabilizes white dwarf stars. For a time, it is sufficient to hold the iron core in equilibrium. However, this form of support has a strict upper limit known as the Chandrasekhar limit. It is named after the astrophysicist Subrahmanyan Chandrasekhar, who worked it out in the 1930s. The limit is about 1.4 times the mass of the Sun. If the mass of a degenerate core rises above this threshold, electron degeneracy pressure cannot resist gravity any longer. The exact number depends on composition and rotation, but the principle is simple. Beyond that limit, the electrons cannot provide enough quantum pressure to balance gravity. For white dwarfs, this marks the dividing line between long-term stability and collapse. For an iron core in a massive star, it is the point where the build-up of material makes further stability impossible. As the iron core approaches, this mass changes occur that weaken its remaining supports. Temperatures in the billions of degrees generate photons with energies high enough to disintegrate iron nuclei. In this process called photodisintegration, a photon strikes an iron nucleus and breaks it into smaller particles such as helium, nuclei, protons and neutrons. The reaction absorbs energy from the core instead of producing it, so the temperature support is reduced. At the same time, the density becomes so great that electrons are forced into protons, a process known as electron capture. When an electron combines with a proton, the result is a neutron and a neutrino. The newly formed neutrinos escape almost immediately, taking energy with them. while the number of free electrons available to resist gravity decreases. These processes happen nearly simultaneously. Photodisintegration saps thermal energy. Electron capture reduces electron pressure. The escape of neutrinos carries away a significant portion of the core's energy. The balance shifts ever more toward gravity. Once the iron core exceeds the Chandrasekhar limit, the fate of the star changes irreversibly. At this moment, the outer layers of the star continue their fusion reactions, but the core is different. It is now a dense sphere with a radius of only a few thousand kilometers, containing more mass than the Sun. Its density reaches billions of grams in every cubic centimeter. Nothing in ordinary matter compares to these conditions. The pressure that once stabilized the star no longer suffices, and the electrons that held up the weight are rapidly disappearing through capture. The state of the star at this point is one of quiet instability. Seen from outside, the star still shines with a red glow, and nothing appears to change. Inside, however, the core is balanced on a knife edge. Its structure of iron nuclei compressed to incredible density is eroded by photodisintegration and electron capture. The Chandrasekhar limit has been reached, and the equilibrium that has lasted through every previous burning stage is gone. The iron core now exists as an object whose weight exceeds the maximum support electron degeneracy pressure can offer. Energy is drained by the breaking apart of nuclei. Electrons vanish into protons. Neutrinos stream out, taking energy away. Gravity dominates, completely pressing inward without counter. The star's outer appearance gives no hint of this interior crisis, yet at the very center, the material is trapped in conditions that cannot remain static. The iron core of a massive star, held for a short time by electron degeneracy pressure, eventually reaches conditions where that pressure can no longer resist gravity. To understand why it is useful to recall the meaning of electron degeneracy itself, electrons are fermions, which means no two of them can occupy the same quantum state. In normal matter, there is space for electrons to move into higher energy levels as atoms interact, but when matter is squeezed to extreme densities, electrons run out of available states. They push back simply because quantum mechanics prevents further compression. This quantum pressure does not depend on temperature, so even if the core cools, it remains in effect. Yet there is a maximum amount of mass that such a sea of electrons can support. The Chandrasekhar limit around 1.4 solar masses defines that maximum. When the iron core crosses it, collapse becomes unavoidable. The physical reason for the limit lies in relativity. At moderate densities, electron pressure increases rapidly as the electrons are forced into higher momentum states. But when the electrons approach the speed of light, their ability to provide additional pressure grows more slowly. The relationship between pressure and density changes. Instead of rising steeply enough to balance gravity, the pressure levels off. The mass that can be supported reaches a ceiling. The iron core of a massive star is therefore destined to fail once enough material has been accumulated from ongoing shell burning. At this stage, the composition of the core is dominated by iron group elements, such as iron 56 and nickel 56. These nuclei have binding energies per nucleon that are among the highest known. No further fusion can provide energy. Instead, as the core temperature rises above billions of degrees, photons carry enough energy to disrupt these nuclei. The reaction of photodisintegration absorbs energy, breaking the nuclei into helium nuclei, protons and neutrons. This effect removes pressure support precisely when it is most needed. At the same time as the density rises, electron capture becomes important. A typical capture occurs when an electron combines with a proton, forming a neutron and emitting a neutrino. This changes the ratio of protons to neutrons, steadily increasing the neutron fraction. Because electrons are removed, the degeneracy pressure weakens. Because neutrinos escape almost instantly, they remove both energy and lepton number from the core. The weakening of pressure support causes the collapse to accelerate. Gravity pulls inward with nothing left to resist it. The entire iron core, with more than a solar mass of material, begins to fall inward in a matter of milliseconds. The velocities increase rapidly, approaching a fraction of the speed of light. During this infall, the density climbs far beyond what is familiar in normal atomic matter. At 1 billion grams per cubic centimeter, atoms are crushed, electrons are stripped, and nuclei are packed tightly. At 10 billion grams per cubic centimeter, electron capture becomes dominant and the neutrino emission becomes immense. At nuclear density about 2.8 times 10 to the 14th grams per cubic centimeter, the neutrons themselves begin to interact strongly, creating an entirely new state of matter. The collapse is not uniform. The inner core, about half the mass of the Sun, contracts nearly homologously, meaning all parts fall at roughly the same rate. The outer core collapses more rapidly. As the density crosses nuclear values, the strong nuclear force begins to resist compression. The innermost region stiffens suddenly. The matter there can be compressed only slightly beyond nuclear density before the repulsion between nucleons becomes overwhelming. When this happens, the collapse of the inner core halts almost instantaneously. The material overshoots slightly and then rebounds. This rebound drives a shock wave outward into the still infalling outer core. The moment of core bounce is extraordinarily brief, lasting only a few milliseconds, but it is decisive in shaping the subsequent evolution. The shock that forms at the interface between the rebounding inner core and the still collapsing outer layers initially has great energy. It pushes outward against the infalling matter, marking the first attempt of the star to explode. However, the shock immediately encounters obstacles. As it moves outward, it must dissociate iron nuclei into free nucleons. This process consumes energy from the shock, reducing its strength. At the same time, the intense emission of neutrinos carries away energy from the post-shock region. The result is that within tens of milliseconds, the shock stalls at a radius of a few hundred kilometers. Although the collapse has been halted in the very center, the outward push of the shock is insufficient on its own to disrupt the star. Instead, a balance is established between the ram pressure of the infalling material and the weakened shock front. Matter continues to rain down, adding to the load. The situation at this point is precarious. The central core has transformed into an extremely hot and dense sphere of neutrons, but it is not yet stable. The proto-neutron star is still contracting, still radiating neutrinos, and still adjusting to its new form. The critical role of neutrinos emerges here. Although they interact weakly, the density inside the proto-neutron star is so high that they scatter many times before escaping. They are produced in abundance by electron capture and by thermal processes. For a short period, the star traps them, allowing their energy to heat the surrounding material. A small fraction of these neutrinos are absorbed behind the stalled shock, depositing energy and raising the pressure. Over several hundred milliseconds, this additional heating may revive the shock, pushing it outward once more. In modern supernova theory, this neutrino-driven mechanism is considered the leading explanation for how the explosion succeeds. At the point we are describing, the story is one of rapid infall and sudden halt. The inner iron core has collapsed to nuclear density in less than a second. The rebound has launched a shock, but the shock has already lost momentum. The proto-neutron star has appeared, but it is still hot, still lepton-rich, and still radiating intensely in neutrinos. The outer layers of the star continue to fall inward, compressing onto the stalled shock. Observationally, nothing is yet visible from outside. The star still appears as a red supergiant. Deep inside, however, the transition from an unstable iron core to a rebounding neutron-rich core has taken place, and the immediate outcome is a stalled shock front held in balance by opposing forces. In the stalled shock region, the dynamics of matter and energy unfold on scales that are difficult to imagine. The shock itself forms a boundary between two very different flows. On one side, matter continues to plunge inward under gravity. On the other side, matter has been compressed and heated, then slowed nearly to rest. At first, the shock possesses enough energy to push outward, but as it forces its way through the dense iron-rich material of the outer core, it loses energy by breaking heavy nuclei into free protons and neutrons. Each iron nucleus requires several tens of millions of electron volts to dissociate, and multiplied by the vast number of nuclei, the total energy drain is immense. This energy comes directly from the shock, which quickly weakens. Within only a few hundred kilometers, the forward motion stalls. The balance that results is fragile. Infalling material continues to rain down from above, carrying momentum that pushes against the shock front. The shock becomes stationary in the sense that it no longer expands outward, instead oscillating as matter strikes it. Behind the shock, a layer of hot, dense plasma forms. This region is sometimes called the gain region, because whether it gains enough energy from neutrinos to revive the shock determines the fate of the explosion. The proto-neutron star lies beneath, still contracting and still radiating neutrinos at extraordinary rates. Neutrinos are produced through several processes during this phase. Electron capture on protons yields electron neutrinos. The inverse process, in which positrons capture on neutrons, yields electron antineutrinos. Thermal processes such as pair annihilation of electrons and positrons create neutrino-antineutrino pairs of all flavors. In total, the proto-neutron star releases on the order of 10 to the 53 ergs in neutrinos over tens of seconds. This is about 100 times the energy radiated in the photons of an entire galaxy during the same interval. Nearly all of the gravitational binding energy of the collapsing core emerges in neutrinos. Although neutrinos interact only weakly, the density near the proto-neutron star is so high that they scatter many times before escaping. Their diffusion time is measured in seconds, which is long compared to the millisecond timescales of the collapse, but short compared to the lifetime of the star. Some of the neutrinos stream out into space almost unhindered. Others deposit a small fraction of their energy into the matter behind the shock. This heating increases the pressure in the gain region. If the heating rate exceeds the cooling rate, the stalled shock can be revived. The physics here is complex and still a subject of active study. Simulations show that convection in the gain region enhances the efficiency of neutrino heating. Hot material rises, cooler material sinks, and this overturning motion increases the residence time of matter in the heating zone. Hydrodynamic instabilities such as the standing accretion, shock instability, create sloshing and spiral motions that also increase efficiency. The result is that neutrino heating can accumulate over hundreds of milliseconds until the shock gains enough energy to push outward once again. Meanwhile, the proto-neutron star itself continues to evolve. It is extremely hot with central temperatures of tens of billions of degrees, and it is dense beyond comparison, exceeding nuclear density in its center. The composition is dominated by neutrons, though some protons and electrons remain along with trapped neutrinos. As electron capture continues, the number of trapped neutrinos rises until they diffuse out. The lepton content gradually decreases, a process known as deleptonization. The star contracts further as it cools, becoming more compact. The neutrino emission is not uniform. Different flavors of neutrinos decouple from matter at different depths, leading to different average energies. Electron neutrinos and antineutrinos typically emerge with energies of about 10 to 15 mega-electron volts, while the heavier muon and tau neutrinos, which interact less, emerge with higher energies of up to 20 or more mega-electron volts. Detectors on Earth are sensitive mainly to electron antineutrinos, so the signal observed from a nearby supernova would be dominated by this flavor. The brief burst of neutrinos observed from supernova 1987A confirmed many of these theoretical expectations. The surrounding layers of the star continue to fall inward, striking the stalled shock. As they do, they are heated and slowed, joining the turbulent gain region. Each packet of matter lingers there long enough to absorb some neutrino energy. If the balance tips far enough, the shock begins to move outward once more. This outward motion must overcome not only the weight of the overlying layers, but also the continued infall. Once the shock gains momentum, it accelerates through the star's mantle, driving the supernova explosion. At this point in the evolution, however, the focus remains on the stalled shock and the neutrino heating that governs its fate. The proto-neutron star beneath contracts and grows denser, its radius shrinking from several tens of kilometers toward around 20 kilometers. The neutrino luminosity peaks at more than 10 to the 51 ergs per second in each flavor, an output greater than the combined electromagnetic luminosity of the entire visible universe at that moment. All of this occurs in the span of a few seconds, a timescale that is minuscule compared to the millions of years the star spent fusing elements. The interaction of these processes defines the structure of the explosion. The gain region convection, hydrodynamic instabilities, and neutrino transport work together to convert a portion of the gravitational energy into kinetic energy of the outward shock. Observational evidence such as the neutrino burst from 1987, the asymmetries in observed supernova remnants, and the energies of explosions all support the basic outline of this mechanism, though details remain debated. The state reached after the collapse is one in which the star's center has transformed into a hot, dense, neutron-rich object surrounded by layers of turbulent plasma. Neutrinos stream outward, carrying nearly all of the gravitational energy released. The shock front remains suspended a few hundred kilometers above the core, neither fully collapsing back inward, nor yet succeeding in racing outward. Within this narrow zone of matter and energy, the eventual course of the event is being determined by the interplay of weak interactions, fluid motions, and gravity. When the inner core reaches nuclear density and rebounds, the outward shock forms, but its initial surge is not enough to eject the outer layers. Instead, the shock loses energy quickly. The main drain comes from photodisintegration of heavy nuclei. As the shock travels through the surrounding iron-rich material, it must break the nuclei into free protons and neutrons. Each nucleus requires about 8 million electron volts per nucleon to split, and multiplied by the vast number of nuclei, the energy cost is enormous. This reduces the shock's momentum until it stalls at a radius of a few hundred kilometers from the center. At the same time, the flood of neutrinos produced during collapse carries away vast amounts of energy. These losses make the shock incapable of immediate explosion. The stalled shock defines a region of intense physical processes. Matter from the outer layers continues to fall inward at supersonic speeds, colliding with the shock front. This matter is decelerated, heated, and compressed, forming a layer of hot plasma behind the shock. In this region, the interplay between neutrino heating and cooling determines whether the shock can be revived. The proto-neutron star below remains extremely hot and dense, releasing neutrinos from its surface layers. Some of these neutrinos pass outward through the hot material and deposit energy. This neutrino heating is the key to the next stage of evolution. The amount of energy deposited depends on both the luminosity and the spectrum of the neutrinos and the density and composition of the matter in the gain region. Electron neutrinos and electron antineutrinos interact most strongly because they can change neutrons to protons and vice versa, releasing or absorbing energy in the process. The absorption of electron neutrinos on neutrons and the absorption of electron antineutrinos on protons deposit heat in the plasma. The balance between these processes and the continuous emission of neutrinos from cooling reactions sets the net energy gain. If heating dominates, the pressure builds and the shock is pushed outward again. If cooling dominates, the shock remains stalled. The behavior of the gain region is strongly influenced by fluid motions. Convection develops because neutrino heating is stronger closer to the proto-neutron star and weaker farther away. This gradient makes the hot matter buoyant while cooler material sinks. Rising plumes and sinking flows mix the region, increasing the time matter spends in the zone where neutrinos are abundant. This extended residence time allows more energy to be absorbed. In addition, large-scale instabilities such as the standing accretion shock instability create oscillations of the shock front. The shock can slosh back and forth or develop spiral modes that redistribute energy and momentum. These hydrodynamic processes enhance the chances of shock revival. Meanwhile, the proto-neutron star continues to change internally. Its central density rises above nuclear saturation density, and the neutrons begin to form a degenerate fluid. Some protons remain, and together with electrons and trapped neutrinos, they define the lepton fraction of the star. Over time, electron capture continues to lower the number of electrons and neutrinos diffuse, outreducing the lepton fraction. This deleptonization alters the pressure balance, causing the proto-neutron star to contract further. Its radius shrinks from perhaps 50 kilometers immediately after bounce to about 20 kilometers within the first second. The temperature remains tens of billions of degrees, ensuring ongoing neutrino production. The neutrino flux emitted during this phase is so intense that it is sometimes described as a neutrino fireball. Yet the vast majority of these particles escape into space, carrying energy away without interacting. Only a small fraction are absorbed behind the shock, but this small fraction is critical. The total energy required to drive the supernova is about 1% of the energy carried by the neutrinos. Thus, even a modest efficiency in energy deposition is sufficient to revive the shock. In this phase, the delicate competition between heating and cooling continues for several hundred milliseconds. If the neutrino heating becomes strong enough, the shock expands again. Once outward motion resumes, it is reinforced by the continued deposition of energy. As the shock pushes outward through the outer core and mantle, the density decreases, and the energy losses from photodisintegration lessen. The shock can then accelerate, transforming into the blast wave that disrupts the star. Observations of supernova remnants support this picture. Asymmetric ejecta and mixing of heavy elements are consistent with the instabilities and convection predicted by simulations. The neutrino burst detected from supernova 1987A also matches the expected emission from a cooling proto-neutron star. These lines of evidence suggest that although the exact mechanism of shock revival is complex, the neutrino heating scenario captures the essential physics. For the proto-neutron star itself, this stage is one of transition. It has passed from a collapsing iron core to a rebounding neutron-rich object surrounded by intense neutrino fluxes. It is still hot, still contracting, and still losing lepton number. Its outer layers are in constant interaction with the shock and the gain region above. The composition of the matter around it is rapidly changing as nuclei are dissociated and reassembled in the hot environment. The turbulence and fluid motions feed back on the neutrino heating, shaping the outcome. The timescales are remarkably short. From the onset of collapse to the formation of the stalled shock is less than 1 second. From bounce to possible shock revival is of order several hundred milliseconds. Yet within these intervals, the core transforms from a stable iron sphere into a compact neutron-rich star and sets the conditions for the explosion of the outer layers. All of this occurs while the outer envelope of the star, far from the center, still appears unchanged to an outside observer. The physical picture at this point is one of balance. The shock no longer advances, yet it is not destroyed. The proto-neutron star radiates enormous numbers of neutrinos. The gain region churns with convection and instabilities. The deposition of a small fraction of neutrino energy may or may not be enough to re-energize the shock. The process is governed by weak interactions, nuclear physics and fluid motions all taking place under the crushing influence of gravity. As neutrinos stream outward from the contracting proto-neutron star, their interaction with matter continues to shape the region around the stalled shock. The neutrino flux carries almost all of the gravitational binding energy released by the collapse, an amount close to 10 to the 53 ergs. While only a small fraction of this energy is absorbed behind the shock, even that fraction is enough to influence the dynamics. Heating from neutrino absorption raises the entropy of the material in the gain region. With higher entropy, matter becomes less tightly bound and easier to lift outward. The competition between gravitational infall and neutrino heating plays out on millisecond timescales, with each new parcel of matter passing through the shock and entering the gain region, before either accreting onto the proto-neutron star or being pushed outward if the shock is re-energized. The microphysics of neutrino interactions is central to this stage. When an electron neutrino encounters a neutron, it can be absorbed, converting the neutron into a proton and releasing an electron. When an electron antineutrino encounters a proton, it can be absorbed, converting the proton into a neutron and releasing a positron. Both processes deposit energy directly into the matter. Because the densities are high, these interactions occur often enough to matter, though the majority of neutrinos still escape. The energy deposition rate depends on the neutrino luminosity, the mean neutrino energy, and the number density of nucleons in the gain region. Another important feature of this phase is the continuous emission of neutrinos from the proto-neutron star itself. The core remains opaque to neutrinos at first, but as it contracts, the neutrinos diffuse outward. Each flavor has a characteristic decoupling radius known as a neutrinosphere, analogous to the photosphere of an ordinary star. Beyond this radius, neutrinos stream freely into space. The temperatures at the neutrinospheres set the average energies of the emerging neutrinos. Electron neutrinos decouple at relatively large radii where temperatures are lower, so they carry lower energies. Muon and tau neutrinos decouple deeper inside, so their average energies are higher. These differences matter because the absorption cross-sections scale with the square of the energy, making higher energy neutrinos more efficient at depositing heat if they interact. Hydrodynamic instabilities continue to grow in the region between the proto-neutron star and the shock. Convection is fueled by the heating gradient, and the standing accretion shock instability produces large-scale sloshing and spiral modes. These instabilities redistribute energy and momentum, lengthening the residence time of matter in the gain region and helping neutrino heating accumulate. Without such instabilities, the efficiency of the energy deposition would be lower, and simulations suggest that explosions would be less likely. The multidimensional character of these instabilities is now seen as essential. Meanwhile, conditions inside the proto-neutron star evolve steadily. As electron capture continues, the number of trapped neutrinos decreases and deleptonization proceeds. This loss of lepton number alters the chemical composition, raising the neutron fraction. The pressure balance changes, causing further contraction. The central density climbs beyond nuclear saturation, and the star cools through neutrino emission. In the inner regions, nuclear matter exists as a hot, dense fluid of neutrons, protons, electrons, and neutrinos. The equation of state, which describes how pressure relates to density and temperature, plays a decisive role. If the nuclear matter is stiff, the proto-neutron star resists contraction more strongly. If it is soft, contraction proceeds further. Current uncertainties in the nuclear equation of state therefore translate into uncertainties in the exact properties of the newborn neutron star. The neutrino burst that occurs during the first few seconds is a striking signature. In less than 10 seconds, the star radiates more neutrinos than the Sun will emit in its entire 10 billion year lifetime. These neutrinos carry information about the internal processes of the collapse. For example, the initial sharp spike of electron neutrinos comes from the sudden burst of electron capture at core bounce. Following that, the sustained emission reflects the cooling of the proto-neutron star. On Earth, neutrino detectors can capture only a small number of these particles from a supernova even in our own galaxy, but the handful observed from supernova 1987 confirmed many predictions of the theory. As the shock remains stalled, accretion of matter from the outer layers continues. Each new shell of material falls inward, passes through the shock, and adds to the weight on the proto-neutron star. This accretion releases gravitational energy which is partly radiated away in neutrinos. The rate of accretion depends on the mass of the star and the structure of its outer layers. In some cases, accretion can tip the balance toward collapse into a black hole if the proto-neutron star gains too much mass. In other cases, neutrino heating succeeds in reviving the shock before that happens. The competition between accretion and heating is one of the central themes in supernova physics. The delicate balance continues for several hundred milliseconds to about a second after core bounce. During this interval, the neutrino luminosity remains extremely high. The proto-neutron star contracts from an initial radius of about 50 kilometers to closer to 20 or 30 kilometers. Its central density rises and its temperature, though decreasing, remains in the tens of billions of degrees. The neutrino mean energies fall gradually as the star cools. The surrounding region remains turbulent with convection and instabilities transporting energy and mixing matter. At larger radii, the outer layers of the star are still unaware of the drama at the core. The envelope, many times the size of Earth's orbit, glows faintly as a red supergiant. The timescales are so short that nothing has yet changed at the surface. Photons take many years to diffuse outward through the opaque layers, so no sign of the collapse has reached the surface. From outside, the star remains calm. Deep inside, however, the competition between gravity nuclear physics, neutrino transport, and hydrodynamic instabilities continues to unfold with extraordinary intensity. In the regions nearest the proto-neutron star, matter is heated by neutrinos until it reaches high entropies. Some of this matter may be ejected in neutrino-driven winds once the shock revives. These winds can play a role in nucleosynthesis, creating elements heavier than iron through rapid neutron capture. The details depend on the conditions of temperature, density, and electron fraction in the outflow. While these nucleosynthesis processes are still under investigation, they highlight the connection between the physics of core collapse and the chemical enrichment of the galaxy. At this stage of the sequence, the proto-neutron star is still forming. It has a dense neutron-rich core, a surrounding hot mantle, and a continuous flux of neutrinos streaming outward. The shock remains at a few hundred kilometers stalled but not collapsed. Matter continues to fall, in neutrino heating continues to deposit energy, and fluid motions continue to stir the gain region. All of these processes occur on timescales of milliseconds, yet they define the fate of the explosion and the nature of the compact remnant. The proto-neutron star, though still in its earlier seconds, already contains matter, compressed to densities exceeding that of atomic nuclei. In this regime, the familiar picture of atoms with electrons orbiting nuclei no longer applies. Instead, the matter is a sea of neutrons with a small fraction of protons and electrons, and for a short time a significant number of trapped neutrinos. The neutrons themselves are fermions, so they also contribute degeneracy pressure. but the conditions are such that their interactions through the strong nuclear force are as important as their quantum exclusion. The nuclear force is attractive at moderate distances but repulsive at very short range. So as the core density rises, the repulsion stiffens the equation of state and halts further collapse. The balance of degeneracy pressure and nuclear repulsion defines the core as a distinct astrophysical object. This object is still not a stable neutron star in the usual sense. Its temperature is tens of billions of degrees, so thermal effects are enormous. It is lepton-rich, meaning that electrons and neutrinos are still abundant compared to the cold neutron stars observed later. The radius remains around 20 to 30 kilometers larger than the 10 to 15 kilometers typical of a cooled neutron star. Over the course of tens of seconds, it will cool and deleptonize, contracting further and settling into its final form. But during these first seconds, it is best described as a proto-neutron star. The neutrino diffusion that drives cooling also changes the chemical composition. As trapped neutrinos escape, the ratio of electrons to baryons decreases. More neutrons form, and the matter becomes increasingly neutron-rich. This process alters the pressure balance, allowing further contraction. The emission of neutrinos follows a characteristic pattern, an initial sharp spike at core bounce, dominated by electron neutrinos, followed by a sustained emission of all flavors as the proto-neutron star cools. The luminosity declines gradually over tens of seconds. Each flavor carries away a comparable share of the energy, though with different average energies. The structure of the proto-neutron star can be described in layers. At the center lies a dense core where neutrons dominate with densities above nuclear saturation. Surrounding this is a mantle of hot, partially dissociated nuclear matter. Beyond that lies the neutrinosphere, a region at which neutrinos last scatter before streaming freely into space. The radius of the neutrinosphere depends on the neutrino flavor, since different flavors interact differently. Electron neutrinos decouple farther out, while muon and tau neutrinos decouple deeper in. The mantle and the region just above the neutrinosphere are heated both by neutrino interactions and by the continued accretion of infalling matter. Accretion onto the proto-neutron star remains an important process in these early seconds. Material from the outer core continues to fall inward, releasing gravitational energy as it strikes the surface layers. This energy is partly converted into neutrinos, which escape, further fueling the neutrino luminosity. The accretion rate depends on the progenitor star's structure. Stars with more massive envelopes supply a larger accretion flow, and in some cases the proto-neutron star can gain so much mass that it exceeds its own stability limit, collapsing into a black hole. The outcome therefore depends on the delicate balance between the rate of accretion, the efficiency of neutrino heating, and the stiffness of the nuclear equation of state. Inside the proto-neutron star, matter is not static. At high densities and temperatures, neutrons may begin to pair up in a way similar to electrons in a superconductor, forming a superfluid. Protons may also form superconducting pairs. These quantum phases of nuclear matter alter the transport of heat and neutrinos, influencing the cooling history. The exact onset of superfluidity and superconductivity depends on the density and temperature, and these remain uncertain. Theoretical models predict that as the proto-neutron star cools over minutes to years, regions of neutron superfluid and proton superconductor will form in its interior. These exotic states are part of the long-term evolution, but the conditions that give rise to them begin in the very first seconds. At the same time, the proto-neutron star possesses an intense magnetic field, amplified during collapse by the conservation of magnetic flux. The contraction of the core squeezes the field lines together, raising the field strength from perhaps 1,000 Gauss in the progenitor star to trillions of Gauss or more in the remnant. Rotation amplifies this further through dynamo processes in the convective layers. In some cases, if conditions are favourable, the magnetic field can reach values of around 10 to the 15th Gauss, producing what astronomers call a magnetar. In the majority of cases, the field is lower but still vastly stronger than anything achievable on Earth. The exact mechanism of amplification is not fully understood, but the interplay of turbulence, convection and rotation in the early proto-neutron star appears to be decisive. Rotation also plays a role in shaping the proto-neutron star. The core of the progenitor star may have been rotating relatively slowly, but as the collapse proceeds, angular momentum is conserved. A reduction in radius by a factor of 1000 increases the rotation rate by the same factor. A core rotating once every day before collapse could spin many times per second afterward. The precise outcome depends on how much angular momentum the star lost during its earlier evolution, which in turn depends on magnetic torques and mass loss through stellar winds. As a result, newborn neutron stars exhibit a range of spin periods from milliseconds to hundreds of milliseconds. These extreme conditions, densities above nuclear temperatures of tens of billions of degrees magnetic fields, trillions of times stronger than Earth's, and spin rates of many rotations per second, define the proto-neutron star as a unique astrophysical object. No other place in the universe combines all of these features in such a small volume. Its formation marks the end of one physical regime governed by electron degeneracy, and the beginning of another governed by neutron degeneracy and nuclear interactions. While the proto-neutron star radiates neutrinos, the outer layers of the progenitor star continue to interact with the stalled or reviving shock. If the neutrino heating is sufficient, the shock expands and accelerates outward. The explosion then ejects the outer layers of the star into space. If not, accretion continues and the proto-neutron star may collapse further. Regardless of the outcome, the proto-neutron star phase itself lasts tens of seconds and sets the initial conditions for the future compact object. In those tens of seconds, most of the gravitational binding energy of the star is carried away in neutrinos. The luminosity falls as the star cools and contracts. The lepton fraction decreases and the composition becomes more neutron-rich. The radius shrinks and the density rises. Internal processes such as the onset of neutron superfluidity and proton superconductivity begin to take shape. Magnetic fields are amplified. Rotation rates are fixed by conservation of angular momentum. Each of these features will influence the later observable properties of the neutron star, such as its spin magnetic field, cooling rate, and emission of radiation. The transformation of the collapsing iron core into a hot proto-neutron star is therefore a process defined by extreme density, neutrino transport accretion, nuclear physics and quantum mechanics. It is a distinct stage of matter in the universe separate from both the original star and the stable neutron star that may emerge later. It is also a stage that cannot be seen directly, but only inferred from neutrino signals and the aftermath of supernova explosions. The proto-neutron star, though compact and extremely dense, is not uniform in its structure. Its outer layers are less dense and hotter, while the inner core is denser and cooler as neutrinos begin to escape. The boundary between the inner and outer regions is marked by gradients in density, temperature, and composition. This stratification is unstable to convection, so matter circulates vigorously. Hotter fluid rises while cooler fluid sinks, transporting heat outward and bringing fresh material into contact with the regions of intense neutrino flux. These convective motions enhance the luminosity of neutrinos and alter the distribution of lepton number throughout the star. In numerical simulations, convection in the proto-neutron star increases the rate at which neutrinos carry away energy and shortens the time required for the object to reach a more stable state. The physical size of the proto-neutron star contracts during this time. Immediately after bounce, its radius may be as large as 50 kilometers, but as neutrinos stream outward and deleptonization proceeds, the star shrinks to about 20 kilometers within a second or two. This contraction releases additional gravitational binding energy, which also emerges as neutrinos. The process is not smooth, but instead involves oscillations of the surface layers, sometimes described as proto-neutron star pulsations. These oscillations can couple to the surrounding medium, producing gravitational waves. While the strength of such gravitational waves is expected to be small, advanced detectors may one day be capable of detecting them from a nearby supernova, providing a new window into the physics of the collapse. The stalled shock, located a few hundred kilometers from the surface of the proto-neutron star, remains the key site where the success or failure of the explosion is decided. Neutrinos emitted from the proto-neutron star interact with matter behind the shock, heating it. This heating raises the entropy of the material, making it buoyant. Rising plumes of hot matter push the shock outward, while cooler material sinks and is reheated. This convective overturning sustains the heating process. If the energy deposition is sufficient, the shock resumes outward motion. Once it gains momentum, the decrease in density with radius reduces the energy cost of further expansion, allowing it to accelerate. Rotation and magnetic fields influence this entire sequence. If the progenitor core was rotating significantly before collapse, the proto-neutron star inherits that angular momentum. Conservation of angular momentum means that a reduction in radius leads to a dramatic increase in spin rate. For example, a core rotating once per day before collapse can rotate many times per second afterward. Rapid rotation alters the dynamics of the collapse, flattening the proto-neutron star into an oblate shape and changing the way neutrinos are emitted. It also provides a reservoir of rotational energy that can in some cases contribute to powering the explosion. Magnetic fields are amplified during collapse by several mechanisms. The simplest is magnetic flux conservation. As the radius of the core shrinks by a factor of about 1,000, the magnetic field strength increases by about 1,000,000. Turbulence and differential rotation within the proto-neutron star can amplify the field further through dynamo action. If the conditions are favorable, the field can reach strengths of 10 to the 15th Gauss, creating a magnetar. More typical newborn neutron stars have fields around 10 to the 12th or 10 to the 13th Gauss. These fields play a role in channeling outflows and in controlling the spin down of the star once it becomes visible as a pulsar. The proto-neutron star continues to accrete material from the overlying layers of the progenitor. This accretion adds mass and supplies additional neutrino luminosity. The accreted matter strikes the surface, is heated to extreme temperatures, and then emits neutrinos as it settles. This process increases the neutrino flux in the first second after bounce. The rate of accretion depends on the density profile of the progenitor star. For some stars, the accretion decreases quickly as the outer layers are less dense. For others, the accretion remains high for longer, delaying the explosion. If too much mass is added to the proto-neutron star, it may exceed the maximum mass allowed by the nuclear equation of state, leading to collapse into a black hole. The fate of the shock is closely tied to the balance between neutrino heating and accretion. If heating wins, the shock moves outward. If accretion dominates, the shock may remain stalled or retreat. Multidimensional effects such as convection and hydrodynamic instabilities improve the chances for heating to succeed. Observations of supernovae suggest that the majority of massive stars do explode, though some may fail and form black holes directly. The diversity of outcomes reflects the sensitivity of the process to initial conditions such as mass metallicity rotation and magnetic field strength. While the proto-neutron star evolves on second timescales, the observable signals on Earth would come first in the form of neutrinos. A burst of neutrinos lasting about 10 seconds is expected from any core collapse event in our galaxy. Following that, once the shock reaches the stellar surface and breaks out, a sudden brightening in electromagnetic radiation occurs. This shock breakout marks the visible start of the supernova, though it may be delayed by hours from the core collapse itself depending on the size of the star. In the meantime, the proto-neutron star continues its transformation, cooling, contracting, and setting the initial conditions for the later neutron star. Inside the proto-neutron star, the physics of dense matter governs the structure. At densities above nuclear saturation, neutrons dominate, but the presence of a small fraction of protons and electrons ensures that beta equilibrium is maintained. Neutrinos are trapped at first, but as diffusion proceeds they escape, and the lepton fraction decreases. The pressure is provided by a combination of neutron degeneracy, nuclear repulsion, and thermal contributions. The equation of state is uncertain, with different models predicting different stiffness. A stiffer equation of state produces a larger radius for the same mass, while a softer one produces a smaller radius. These differences affect the neutrino emission, the gravitational wave signal, and the maximum mass of the neutron star. The proto-neutron star thus represents a laboratory of extremes. It contains matter at densities and temperatures unreachable on Earth, governed by interactions that are only partly understood. Its rapid evolution in the first seconds after bounce sets the stage for either the success of the supernova explosion or the quiet collapse into a black hole. Though invisible to direct observation, it reveals itself through neutrino emission gravitational waves and the remnants left behind after the explosion. The neutrino-driven mechanism remains the leading explanation for how a stalled shock wave in core collapse is revived. Yet the details of how it functions depend on processes occurring on very small and very large scales at once. At the microscopic level, the rates of neutrino interactions with neutrons and protons determine how much energy is deposited. At the macroscopic level, the motions of entire regions of matter shaped by convection and global instabilities determine how efficiently that energy is retained. Numerical simulations in multiple dimensions show that the gain region behind the shock is rarely smooth. Instead, it churns with rising bubbles of hot matter and sinking streams of cooler matter. These overturning flows allow neutrino heating to be more effective because matter spends more time in regions of high neutrino flux before either falling onto the proto-neutron star or being swept outward. The standing accretion shock instability is one of the most striking features of this regime. It is an instability of the stalled shock that produces large-scale oscillations. The shock can slosh from side to side or develop spiral modes that rotate around the core. These oscillations modify the geometry of the gain region, changing how matter interacts with neutrino heating. When combined with convection, the instability creates a highly dynamic environment. Such instabilities are thought to be responsible for the asymmetric shapes observed in many supernova remnants, where ejecta are not distributed evenly, but show strong clumping and directional flows. The proto-neutron star beneath the shock continues to contract. Its central density rises further. Its temperature decreases gradually as neutrinos carry energy away, and its radius shrinks toward around 15 to 20 kilometers. The pressure inside comes increasingly from neutron degeneracy and nuclear repulsion, while thermal contributions decline as the star cools. The composition also changes. The electron fraction decreases as electron capture proceeds, leaving matter more neutron-rich. The trapped neutrinos that dominated in the first fraction of a second diffuse out so the lepton number falls. Over several seconds, the proto-neutron star thus evolves toward the structure of a stable neutron star. The neutrino luminosity remains high during this entire period. At first, right after bounce, the luminosity exceeds 10 to the 52 ergs per second for each flavor. Over the next few seconds, it decreases but remains intense. The emission is approximately balanced between electron neutrinos, electron antineutrinos, and the heavier muon and tau flavors. The energies differ with muon and tau neutrinos, having higher average energies because they decouple deeper within the star. On Earth, detectors are mainly sensitive to electron antineutrinos through inverse beta decay on protons. A handful of neutrino events observed from Supernova 1987A matched the predictions of such models, providing rare direct evidence of the processes inside a proto-neutron star. As the shock gains renewed energy through neutrino heating, it can begin to move outward again. Once expansion starts, the density ahead of the shock decreases, reducing the energy lost to photodisintegration. This positive feedback allows the shock to accelerate. The outflowing shock carries with it the elements synthesized in the outer layers of the progenitor as well as the products of explosive nucleosynthesis that occur as the shock heats the stellar material it traverses. This process is responsible for creating many of the elements heavier than iron, including some of the isotopes of nickel and cobalt. Observations of supernova spectra reveal these freshly synthesized elements, confirming that they are forged in the explosion itself. The success of the explosion depends on conditions that vary between stars. A more massive star with a dense envelope supplies a higher accretion rate, which can weigh down the shock and make revival harder. A less massive star allows the shock to expand more easily. Rotation and magnetic fields add further diversity. Rapid rotation can alter the geometry of the collapse funneling matter along the poles. Strong magnetic fields can channel outflows and provide additional energy through magnetic stresses. In extreme cases, these factors may produce particularly energetic explosions or jets, but in ordinary cases, neutrino heating remains the central driver. During this same period, the proto-neutron star experiences continued accretion from the overlying layers. This accretion adds to its mass and increases its neutrino luminosity. If the final mass of the proto-neutron star exceeds the maximum mass allowed by the nuclear equation of state collapse to a black hole ensues. The maximum mass is thought to be between about 2 and 3 solar masses depending on the stiffness of nuclear matter. If the mass remains below this threshold, the star stabilizes as a neutron star. The distinction between these outcomes is delicate depending on details of progenitor structure, rotation, metallicity, and the nuclear equation of state. Inside the proto-neutron star, the conditions are extreme enough to allow the emergence of exotic phases of matter. The high density may cause neutrons to pair into a superfluid, lowering the viscosity and altering the way heat is transported. Protons may pair into a superconducting state, changing the way magnetic fields evolve. At even higher densities, some theories predict that matter could transition into deconfined quarks or hyperons, though whether such transitions occur in nature is still debated. The presence or absence of such exotic matter influences the equation of state, and thus the maximum mass. The interplay of neutrinos' accretion rotation and magnetic fields during this stage leaves imprints that can persist into the later life of the neutron star. The magnetic field strength set during the proto-neutron star phase determines whether the star will be observed as a magnetar or as a more ordinary pulsar. The rotation rate fixed by angular momentum conservation defines the initial spin period of the pulsar. The amount of fallback accretion from material that fails to escape influences the final mass. All of these properties trace back to the physics of the first few seconds after collapse. From the perspective of an external observer, The star's surface still appears unchanged during the early proto-neutron star phase, because photons cannot escape quickly from the outer envelope. Only neutrinos provide direct evidence of the inner processes, and they emerge in a burst lasting about 10 seconds. After that, once the shock wave propagates to the surface, the star brightens suddenly in visible and ultraviolet light. This marks the appearance of the supernova to telescopes, but by then the proto-neutron star has already undergone its critical transformations. The structure at this point can be summarized by describing the zones around the core. At the center lies the proto-neutron star with a radius of tens of kilometers and densities above nuclear. Above it lies the turbulent gain region where neutrino heating occurs. Farther out lies the shock front, stalled or moving outward depending on the balance of heating and accretion. Beyond that lie the still in falling outer layers of the star. This stratification evolves rapidly, with each zone influencing the others. The proto-neutron star's evolution in these early seconds thus involves contraction, deleptonization, neutrino emission, and interaction with accreting material. The stalled shock interacts with neutrino heating convection and instabilities, while the outcome depends on the star's initial mass and structure. Magnetic fields and rotation provide further channels of influence. In this dense, hot and dynamic environment, the newborn neutron-rich object continues to cool and contract, while its surroundings determine whether the explosion succeeds and what kind of compact remnant will ultimately remain. As the proto-neutron star radiates away its binding energy in neutrinos, the shock wave outside either continues to expand or hovers near a balance point depending on how effective neutrino heating remains. If the shock expands, it begins to travel through the outer mantle of the star. As it does so, the density and temperature behind the shock rise to levels that trigger additional nuclear burning. This explosive nucleosynthesis produces elements not created during the star's earlier hydrostatic burning phases. For instance, silicon and oxygen layers traversed by the shock are heated so strongly that they undergo fusion reactions on rapid timescales, generating isotopes such as nickel-56. The radioactive decay of nickel-56 to cobalt and then to iron powers the light curve of the subsequent supernova, producing the characteristic rise and fall of brightness observed in many events. The deposition of neutrino energy behind the shock continues even as the shock moves outward. The gain region remains active until the shock has traveled far enough that the density drops and neutrino absorption becomes negligible. For several hundred milliseconds, neutrino heating and convection supply momentum that helps the shock overcome the inertia of the outer layers. Once the shock has cleared the dense core and mantle, the balance shifts decisively toward expansion. The ejected matter carries with it both the products of explosive nucleosynthesis and the heavier elements synthesized in the progenitor's late stages. These ejecta seed the interstellar medium with oxygen, silicon, sulfur, calcium ion, and other heavy elements enriching future generations of stars and planets. Meanwhile, the proto-neutron star continues to contract and cool. Its radius shrinks toward around 15 kilometers, and its density rises further. Neutrinos of all flavors continue to stream outward, with luminosities declining as the star loses energy. During the first 10 seconds after collapse, the proto-neutron star radiates almost all of its binding energy. After that, neutrino emission continues at a lower level for tens of seconds more. The loss of energy through neutrinos is accompanied by a reduction in temperature and entropy. As the star cools, the matter inside begins to undergo phase transitions. Neutrons may pair into a superfluid, and protons may form a superconducting state. These transitions change the way neutrinos are emitted and the way heat is conducted, but they occur gradually as the temperature falls. The fate of the ejected matter is tied to the energy of the explosion. If the explosion energy is high, nearly all of the outer layers are expelled. If the explosion energy is weaker, some of the outer material may fail to escape the gravitational pull of the compact remnant and fall back onto it. This fallback accretion can add mass to the proto-neutron star. In some cases, it may be small, altering the surface composition and magnetic field of the neutron star. In other cases, it may be substantial, increasing the mass enough to drive collapse into a black hole. The amount of fallback depends on the energy of the explosion, the structure of the progenitor, and the distribution of asymmetries in the ejector. Asymmetries are a natural consequence of the instabilities that shape the shock revival. Convection and the standing accretion, shock instability, produce uneven outflows. These asymmetries persist into the expanding ejector, creating clumps and high-velocity flows in some directions. Observations of young supernova remnants show knots of iron-rich material moving at different speeds consistent with such instabilities. These asymmetries also impart a recoil to the compact remnant. Conservation of momentum requires that if more ejecta are expelled in one direction, the proto-neutron star must move in the opposite direction. This mechanism is thought to produce the high space velocities observed in many pulsars, sometimes hundreds of kilometers per second. Magnetic fields and rotation contribute further complexity. A rapidly rotating proto-neutron star with a strong magnetic field can channel energy into polar outflows. In extreme cases, this may produce a jet-driven explosion. Such events are associated with the most energetic supernova and with long-duration gamma-ray bursts. In ordinary cases, the fields are not strong enough to dominate the dynamics, but they still influence the distribution of matter and the subsequent spin-down of the neutron star. The strength of the magnetic field and the initial spin period are imprinted during this early phase, and will shape the observational properties of the neutron star as it emerges from the cooling proto-neutron star phase. The nuclear equation of state remains a central uncertainty throughout. If the equation of state is stiff, the proto-neutron star has a larger radius for a given mass, leading to different neutrino spectra and different maximum masses. If it is soft, the star is more compact with higher central densities. These differences affect the gravitational wave emission, the neutrino signals, and the likelihood of black hole formation. Observational constraints from neutron star masses, radii, and cooling curves are gradually narrowing the possibilities, but the exact behavior of matter at several times nuclear density remains unknown. While the proto-neutron star contracts and cools, the outer shock continues to propagate through the progenitor star. When it reaches the stellar surface, the sudden release of trapped photons produces the shock breakout. This brief flash of ultraviolet and X-ray radiation lasts only minutes to hours depending on the radius of the progenitor. Afterward, the expanding ejector cool and the supernova light curve rises as radioactive heating from nickel decay takes over. To observers, this bright display is the visible signature of the explosion, but the processes that created it all occurred in the hidden core seconds earlier. Gravitational waves provide another potential messenger from this phase. The rapid motions of matter in the gain region, the oscillations of the proto-neutron star, and the asymmetries of the shock all produce time-varying quadrupole moments that emit gravitational radiation. The expected amplitudes are small, but within the sensitivity of current and future detectors for a nearby supernova. Detecting such a signal would provide direct information about the hydrodynamic instabilities and the equation of state of nuclear matter. In the minutes after the explosion, the proto-neutron star continues to lose heat through neutrino emission. The cooling drives further contraction until the star reaches its final stable radius. The surface temperature falls from tens of billions of degrees to a few billion degrees, and then over hours to millions of degrees. As it cools, the star's crust begins to form. This crust consists of nuclei arranged in a lattice supported by electron degeneracy pressure overlying the dense core of neutrons. The crust formation marks the transition from the hot proto-neutron star to the cold neutron star observed in the galaxy. The evolution through these seconds and minutes determines the fundamental properties of the neutron star, its mass, radius, spin, and magnetic field. It also determines whether the remnant survives as a neutron star or collapses into a black hole. Each outcome is the product of processes governed by neutrino transport nuclear physics, fluid dynamics, and gravity, all acting together in the heart of a massive star. As the proto-neutron star cools and contracts, its emission of neutrinos gradually declines, yet the flux remains intense compared to ordinary stellar processes for tens of seconds. This long tail of neutrino radiation continues to carry away heat and lepton number. During this period, the deleptonization of the core reaches completion, leaving matter composed primarily of neutrons, with a smaller fraction of protons and electrons. The cooling process reduces the entropy of the star, and the thermal pressure that once contributed significantly to its support becomes negligible compared to neutron degeneracy pressure and nuclear interactions. By the end of this stage, the star transitions into what can be described as a stable neutron star with a radius of roughly 10 to 15 kilometers and a central density several times nuclear saturation. The transition from proto-neutron star to neutron star is accompanied by structural changes. A solid crust forms as the temperature falls to below 1 billion degrees. This crust begins with heavy nuclei arranged in a lattice surrounded by a sea of relativistic electrons. Deeper layers of the crust include exotic arrangements of nucleons known as nuclear pastor phases, where competition between nuclear attraction and Coulomb repulsion produces rod-like, sheet-like, or more complex structures. These unusual configurations affect the thermal and transport properties of the crust and may influence how the star cools over thousands of years. The core beneath the crust remains a dense fluid of neutrons with a small admixture of protons and leptons. The neutrino burst emitted during the first tens of seconds leaves an imprint on the surrounding medium. The neutrino heating that re-energized the shock may continue to drive a neutrino wind from the surface of the proto-neutron star. This outflow is composed of nucleons that absorb enough energy to escape the gravitational well. Such winds are sites of nucleosynthesis producing light elements like lithium and boron, and possibly contributing to the creation of heavy elements through rapid neutron capture if the conditions are neutron-rich enough. The exact role of neutrino-driven winds in galactic chemical enrichment is still debated, but they illustrate the continuing influence of neutrino physics even after the main explosion is underway. The rotational and magnetic properties of the neutron star are largely fixed during this early cooling phase. Conservation of angular momentum during collapse sets the spin period. If the progenitor core retained significant angular momentum, the newborn neutron star may rotate several hundred times per second. If angular momentum was lost through magnetic torques or winds earlier in its life, the spin period may be longer, closer to tens or hundreds of milliseconds. The magnetic field strength results from flux conservation and possible dynamo amplification in the turbulent proto-neutron star. Values can range from around 10 to the 12th Gauss for ordinary pulsars to around 10 to the 15th Gauss for magnetars. These enormous magnetic fields determine how the star interacts with its surroundings once the ejecta clear and the neutron star becomes observable as a pulsar. The birth of a pulsar is closely linked to the cooling proto-neutron star. As the magnetic field and rapid rotation combine, the star begins to lose rotational energy through electromagnetic radiation. This magnetic dipole radiation slows the rotation, gradually converting rotational energy into a particle wind and radiation. The initial spin and magnetic field strength therefore set the luminosity and lifetime of the pulsar phase. Observations of young pulsars such as the Crab pulsar with a spin period of about 33 milliseconds and a magnetic field of about 10 to the 12th Gauss illustrate how these parameters shape observable properties. Magnetars with their far stronger fields display bursts of X-ray and gamma-ray emission powered by magnetic energy rather than rotation. The process of fallback accretion continues to influence the remnant after the explosion begins. Some fraction of the outer layers may not achieve escape velocity and instead falls back toward the compact object. Depending on the amount this fallback can alter the magnetic field by burying it under accreted material change, the spin period by transferring angular momentum or increase the mass of the neutron star. If the accreted mass is large enough, it can push the neutron star over its maximum stable mass, resulting in collapse into a black hole. The likelihood of such an outcome depends strongly on the progenitor's mass and structure, as well as the energy of the explosion. The observable signature of these processes is complex. In addition to the initial neutrino burst and the later supernova-like curve, gravitational waves may be emitted from oscillations of the proto-neutron star from anisotropies in the explosion and from fallback accretion. Detecting such signals would provide direct information about the internal structure and evolution of the remnant. While current detectors are limited, future instruments may capture gravitational waves from core collapse events, revealing details inaccessible through light or neutrinos alone. The neutron star that emerges from this evolution is a compact object unlike anything else in the universe. With a mass comparable to the Sun compressed into a sphere only tens of kilometers across its average density, is greater than that of an atomic nucleus. A teaspoon of neutron star matter would weigh billions of tons on Earth. The surface gravity is so intense that the escape velocity is about half the speed of light. The magnetic field is so strong that it alters the structure of atoms, confining electrons to narrow cylinders along field lines. The rotation is so rapid that the star's surface moves at a significant fraction of the speed of light. These conditions combine to produce observable phenomena such as pulsar beacons, magnetar flares, and gravitational wave signals from oscillations or mergers. Yet these observable features are the end result of the violent processes that occur in the first tens of seconds after collapse. The cooling and deleptonization of the proto-neutron star, the formation of the crust, the amplification of magnetic fields, the conservation of angular momentum, and the interplay of fallback accretion all determine the characteristics of the neutron star that will be studied for millions of years. Each young neutron star thus carries within its properties a record of the supernova explosion that created it. The connection between the microphysics of dense matter and the macroscopic outcome of the explosion underscores the importance of the proto-neutron star stage. The behavior of nuclear matter at densities several times higher than atomic nuclei, the rates of neutrino interactions, and the influence of instabilities in the gain region all feed into the observable properties of the explosion and the remnant. Progress in understanding requires a combination of theoretical modeling, numerical simulations, and observations of supernovae, neutron stars, and neutrinos. The limited neutrino detections from past supernovae already confirm many aspects of the theory, and the hope for a future galactic supernova lies in the possibility of capturing thousands of neutrinos, providing unprecedented detail about the birth of a neutron star. The long-term stability of the neutron star depends on the equation of state of dense matter, which dictates how pressure responds to density at supranuclear values. The central density of a neutron star can exceed several times the density of an atomic nucleus, a regime that cannot be reproduced in terrestrial laboratories. Theoretical models must therefore extrapolate from nuclear experiments and quantum chromodynamics. A stiff equation of state resists compression, yielding larger radii for a given mass and allowing higher maximum masses. a soft equation of state compresses more easily, producing smaller radii and lower maximum masses. Observations of neutron stars with masses above 2 solar masses already constrain the equation of state to be relatively stiff, but whether exotic particles such as hyperons, meson, condensates, or deconfined quarks appear in the core remains uncertain. Within the cooling neutron star, neutrons are expected to form a superfluid and protons a superconductor. In a neutron superfluid, neutrons pair through attractive interactions into states that behave collectively, allowing them to flow without viscosity. In a proton superconductor, protons pair into states that expel magnetic flux through quantized vortices. These quantum phases alter the star's thermal and rotational evolution. Superfluid neutrons reduce the star's heat capacity and modify neutrino emission processes, influencing the cooling curve. Proton superconductivity affects how magnetic fields are anchored and evolve. Observations of cooling rates and magnetic field decay provide indirect evidence for these exotic phases, though direct confirmation remains elusive. As the crust solidifies, its properties become important for the star's behavior. The outer crust consists of heavy nuclei embedded in a sea of electrons. At greater depths, the nuclei become more neutron-rich until they dissolve into the inner crust, where free neutrons coexist with nuclear clusters. Between the crust and the liquid core lies the nuclear pasta region, where competition between nuclear attraction and Coulomb repulsion leads to unusual structures shaped like rods, slabs, and other configurations. These structures influence thermal conductivity, neutrino opacity, and the star's response to stresses. Starquakes in the crust caused by shifting stresses in the magnetic field may explain bursts observed from magnetars. The rotation of the neutron star interacts with its internal superfluid in distinctive ways. The superfluid carries angular momentum in quantized vortices, each a microscopic tube around which the superfluid circulates. As the star spins down, vortices must move outward to reduce the rotation rate. If they become pinned to the crust or to flux tubes in the superconducting core, they can accumulate. When they suddenly unpin, angular momentum is transferred abruptly to the crust, producing a glitch, an observed sudden increase in the spin frequency of pulsars. These glitches provide evidence for superfluidity in the interior, and are among the few direct observational probes of the star's microphysics. The magnetic field established during the proto-neutron star phase shapes the neutron star's external environment. Field strengths of 10 to the 12th or 10 to the 13th Gauss are typical for ordinary pulsars. These fields, combined with rotation, drive a wind of relativistic particles and produce beams of electromagnetic radiation. As the star rotates, the beams sweep through space, and if aligned with Earth, they are observed as pulses of radio X-ray or gamma rays. Stronger fields of 10 to the 15th Gauss define magnetars, which display bursts of high-energy radiation powered by the decay of magnetic energy rather than rotation. The origin of such strong fields is still debated, with dynamo amplification during collapse and fossil fields from the progenitor both proposed. The rotational energy of the neutron star provides another reservoir of power. A star with a millisecond period contains more rotational energy than the entire explosion energy of the supernova. This energy is lost over time through magnetic dipole radiation and particle winds slowing the rotation. The rate of spin down depends on the field strength and geometry. Observations of young pulsars show a range of initial periods from a few milliseconds to hundreds of milliseconds, reflecting differences in progenitor rotation and angular momentum loss. Fullback accretion continues to play a role even after the supernova shock has emerged. Material that failed to escape the gravitational pull of the neutron star eventually returns. Some of it may settle onto the surface, altering the composition of the crust. Some of it may form a disk which can transfer angular momentum and influence the spin. In cases where fallback is heavy, the additional mass can drive the neutron star over the maximum mass limit, leading to delayed collapse into a black hole. This possibility explains why some massive progenitors leave behind black holes without a visible supernova. The threshold between neutron star survival and black hole formation depends sensitively on the nuclear equation of state and the efficiency of the explosion. The cooling neutron star emits neutrinos not only in the first tens of seconds but also over thousands of years. In the early phase, modified Urca processes dominate in which a neutron decays into a proton-electron and antineutrino with the help of a bystander nucleon to conserve momentum, and the reverse process occurs as well. In the presence of superfluidity, additional processes called Cooper pair breaking and formation can emit neutrinos. These neutrino cooling processes exceed photon cooling until the star is several 100,000 years old. Observations of thermal X-ray emission from young neutron stars provide tests of these cooling models and constrain the internal composition. Gravitational waves provide another channel for probing the neutron star. If the star is not perfectly spherical, its rotation produces time-varying quadrupole moments that radiate gravitational waves. Asymmetries can be caused by mountains in the crust, strong internal magnetic fields, or R-mode oscillations in the fluid. Continuous gravitational wave emission has not yet been detected, but ongoing searches target young, rapidly rotating neutron stars. Detection would reveal information about the internal structure and equation of state. The properties of neutron stars are also tested in binary systems. When paired with a companion, accretion of matter can spin up the neutron star to millisecond periods. In such systems, the magnetic field is often reduced either by burial under accreted material or by decay over time. These recycled pulsars demonstrate how external conditions alter the long-term evolution. They also show that neutron stars can survive for billions of years, long after their formation in a supernova. From the perspective of stellar evolution, the formation of a neutron star represents the transformation of gravitational energy into neutrino energy, the rearrangement of nuclear matter into new phases, and the creation of a compact remnant with extraordinary physical conditions. The first minutes after collapse fix the mass-radius spin and magnetic field. The following years reveal the cooling curve, the glitch behavior, and the magnetic activity. Observations across all these timescales provide the evidence needed to test theoretical models of dense matter and supernova explosions. The nuclear equation of state not only determines the maximum mass and radius of a neutron star, but also shapes its internal layering. Near the center, matter is compressed to several times nuclear saturation density, where the pressure is dominated by interactions among neutrons and protons. At these densities, some models predict the presence of hyperons particles containing strange quarks, while others allow for a transition to deconfined quark matter. Each possibility softens the equation of state and reduces the maximum mass. Observations of neutron stars with masses greater than 2 solar masses challenge these soft equations of state, suggesting that if exotic particles appear, they must be balanced by additional repulsive forces. Moving outward from the core, the density decreases and the matter becomes less extreme. At densities slightly above nuclear neutrons may form a superfluid and protons a superconductor. These quantum states modify the heat capacity, the neutrino emission processes, and the response to rotation. The presence of superfluidity is supported by pulsar glitches, which are sudden jumps in rotation rate, interpreted as the unpinning of superfluid vortices from the crust. Superconducting protons, on the other hand, confine magnetic fields into quantized flux tubes. The interaction between neutron vortices and proton flux tubes may play a role in glitch recovery and in the long-term evolution of the magnetic field. Farther out, the density falls below nuclear and nuclei reappear. In the inner crust, nuclei are immersed in a sea of free neutrons. The arrangement of nucleons in this region is influenced by competing nuclear and Coulomb forces, producing complex structures collectively known as nuclear pasta. These shapes, rods, slabs, and more intricate geometries affect how heat and electrons move through the crust. The properties of nuclear pasta are uncertain, but are thought to influence phenomena such as crust cooling in accreting neutron stars and the damping of oscillations in magnetar flares. Above the inner crust lies the outer crust composed of heavy nuclei in a lattice supported by degenerate electrons. The crust plays an important role in the observable behavior of neutron stars. Starquakes occur when stresses in the crust built up by changes in the magnetic field or by spin down are suddenly released. These quakes may explain bursts of high-energy radiation from magnetars. They may also generate gravitational waves if they produce asymmetries in the star's shape. The elastic properties of the crust combined with the stresses imposed by magnetic fields and rotation therefore influence both electromagnetic and gravitational signals. The magnetic field itself evolves as the star cools. Ohmic dissipation, Hall drift, and ambipolar diffusion all contribute to field decay on timescales from thousands to millions of years. In magnetars, the decay of a magnetic field of 10 to the 15th Gauss releases enough energy to power recurrent bursts and flares observed in X-rays and gamma rays. In ordinary pulsars, the weaker fields decay more slowly, leading to long lifetimes as radio sources. The evolution of the field depends on the conductivity of the crust and the presence of superconductivity in the core. The rotation of the neutron star also changes over time. Magnetic dipole radiation and particle winds carry away angular momentum, causing the spin to slow. The rate of spin down is described by the breaking index, which reflects the torque law. Observations show that the breaking index often differs from the simple dipole prediction, suggesting that additional processes such as field evolution or wind torques contribute. Young pulsars spin down rapidly, losing a significant fraction of their rotational energy in tens of thousands of years. Millisecond pulsars spun up later in binary systems can maintain rapid rotation for billions of years. The thermal evolution of the neutron star is governed by neutrino cooling in the first 100,000 years, and photon cooling from the surface afterward. Neutrino emission dominates at high internal temperatures with modified Urca and Cooper pair processes carrying energy out of the core. Once the temperature falls below about 1,000,000 degrees, photon emission from the surface becomes dominant. Observations of thermal X-rays from young neutron stars provide measurements of surface temperature, which can be compared with cooling models. Discrepancies reveal the influence of superfluidity, superconductivity, and exotic particles in the core. Gravitational waves offer another probe of the internal physics. If the star develops a permanent deformation even as small as a mountain only centimeters high, it will radiate continuous gravitational waves as it rotates. Searches for such signals target nearby young pulsars with rapid rotation, though no detection has yet been made. R-mode oscillations, fluid waves driven unstable by gravitational radiation, are another potential source. If they occur, they could limit the maximum spin rate of neutron stars. Detecting such gravitational waves would provide direct evidence of the fluid dynamics and viscosity in the dense interior. In addition to isolated neutron stars, binary systems reveal important aspects of their physics. When a neutron star accretes matter from a companion, it can be spun up to millisecond periods, becoming a recycled pulsar. Accretion also heats the crust and changes its composition, altering its thermal response. Observations of crust cooling in accreting transients after accretion halts have been used to study heat conduction and nuclear reactions in the crust. Binary systems also provide opportunities to measure neutron star masses with high precision constraining the equation of state. The merger of two neutron stars represents an extreme extension of their physics. In such events, gravitational waves carry away orbital energy, while the collision itself produces heavy element nucleosynthesis and electromagnetic counterparts. The detection of both gravitational waves and light from a neutron star merger in 2017 confirmed predictions about these events and provided new constraints on the equation of state. Although mergers occur long after the birth of the neutron stars, their outcome is set by the properties established in the first seconds of collapse. Through all of these phenomena, the neutron star remains a record of the processes that created it. The density profile, the composition of the crust and core, the strength of the magnetic field, the spin period and the mass are all determined during the transition from proto-neutron star to neutron star. Later evolution modifies these properties, but the imprint of the formation remains. Studying neutron stars in all their manifestations, pulsars, magnetars, accretors, and merger participants, therefore provides information about the supernova explosions that created them and the physics of matter at the highest densities known. The rotation and magnetic field of a newborn neutron star create a unique environment for the emission of radiation and particles. As the star spins, its magnetic field co-rotates with it, sweeping through space like a giant dynamo. The misalignment of the magnetic axis and the rotation axis means that beams of electromagnetic radiation emerge from the magnetic poles. When these beams cross the line of sight to Earth, they are observed as pulses, giving rise to the term pulsar. The pulse period is simply the rotation period of the neutron star, ranging from a few milliseconds for the fastest spinning examples to several seconds for the slowest. The emission is powered by the gradual loss of rotational energy carried away by magnetic dipole radiation and relativistic winds of electrons and positrons. The spin down of a pulsar is measured by its breaking index, which describes how the spin frequency decreases with time. In the simplest model, where the torque is dominated by magnetic dipole radiation, the breaking index is 3. Observations, however, reveal that many pulsars have breaking indices lower than 3, indicating additional torque mechanisms at work. Particle winds, changes in the magnetic field structure, or currents in the magnetosphere may all contribute. The breaking index thus provides a window into the dynamics of the magnetosphere and the evolution of the field. Magnetars are a distinct subclass of neutron stars with magnetic fields as high as 10 to the 15th Gauss. In these objects, the decay of the magnetic field provides the main source of energy, powering bursts and flares in X-rays and gamma rays. The stresses induced by such intense fields can fracture the crust, releasing energy in starquakes that trigger giant flares. These events are among the most energetic explosions observed in our galaxy, apart from supernovae, and are detectable across great distances. Magnetars demonstrate how the conditions set in the proto-neutron star phase can lead to very different observable phenomena depending on the magnetic field strength. The diversity of neutron star behavior extends further in binary systems. When paired with a companion star, a neutron star can accrete matter, forming an accretion disk. Material in the disk spirals inward, releasing gravitational energy as X-rays. Such systems are observed as X-ray binaries. In some cases, the accretion torque spins the neutron star up, producing millisecond pulsars. In others, the accretion buries the magnetic field under newly deposited material, reducing its surface strength. Accreting neutron stars therefore illustrate how the external environment modifies the long-term evolution of the star. The maximum mass of a neutron star remains a crucial unknown. If the star accretes too much matter, it can surpass the stability threshold and collapse into a black hole. Observations of the most massive neutron stars provide lower limits to this maximum. Stars with masses around 2 solar masses are known, ruling out many soft equations of state. The upper limit is harder to establish, but if it is below about 3 solar masses, then the collapse to a black hole becomes inevitable for more massive remnants. This maximum mass depends directly on the behavior of dense matter and is constrained by both observations and theory. The surface of the neutron star is another arena of extreme physics. The gravitational acceleration is about 100 billion times that of Earth, so atoms are flattened into thin layers. The magnetic field modifies the motion of electrons, confining them to narrow cylinders along field lines. The atmosphere is only centimeters thick, composed of hydrogen, helium, or heavier elements depending on the star's history. The thermal radiation emitted from the surface carries information about the interior cooling. Observations of surface temperatures over time reveal the efficiency of neutrino cooling processes and the onset of photon cooling. Cooling curves of neutron stars show that different stars follow different tracks depending on their mass composition and superfluid properties. Rapid cooling can occur if direct Urca processes are allowed, where a neutron directly decays into a proton-electron and antineutrino without a bystander nucleon. This process requires a high proton fraction and occurs only in sufficiently massive stars. Slower cooling occurs through modified Urca processes. Observations of young neutron stars suggest that both modes occur, pointing to a range of compositions and confirming the presence of superfluidity. The neutron star in Cassiopeia A, for example, shows a rapid decline in temperature consistent with the onset of neutron superfluidity and associated neutrino emission from Cooper pair breaking. The spin of a neutron star interacts with its interior superfluid through quantized vortices. These vortices carry the angular momentum of the superfluid and must move outward as the star spins down. If they become pinned to the crust or to magnetic flux tubes in the core, they can accumulate stress. When they unpin, suddenly angular momentum is transferred abruptly to the crust, producing a glitch. Pulsar glitches have been observed in many systems, with the Vela pulsar being a prominent example. These glitches reveal the coupling between the crust and the superfluid interior and provide rare insight into the microphysics of dense matter. Gravitational waves from neutron stars may arise not only from mergers, but also from isolated stars. If the star is not perfectly spherical, its rotation produces continuous gravitational radiation. Even tiny deformations can produce detectable signals if the rotation is rapid enough. Searchers target known pulsars, especially young and nearby ones. Although no continuous waves have yet been detected, upper limits already constrain the size of possible deformations. Detection in the future would provide a direct probe of the star's interior crustal strength and magnetic field configuration. The study of neutron stars thus links astrophysics, nuclear physics, and particle physics. Observations of pulsars reveal rotation and magnetic field evolution. Measurements of cooling provide constraints on superfluidity and neutrino processes. Accreting systems show how external conditions alter the crust and magnetic field. Mergers reveal the behavior of matter at the highest densities and produce heavy elements through rapid neutron capture. Each aspect of neutron star physics traces back to the violent birth of the star in a supernova and the rapid evolution of the proto-neutron star. The interplay between rotation magnetic fields, accretion cooling, and dense matter makes neutron stars among the most diverse and informative objects in astronomy. They preserve in their properties the record of the processes that formed them, and they continue to evolve under the influence of fundamental physics. Through careful observation across the electromagnetic spectrum, through neutrino detection, and through gravitational wave astronomy, the study of neutron stars provides answers to questions about matter and gravity that cannot be addressed in any other way. As the neutron star emerges from the proto-neutron star phase, Its continuing interaction with the material around it defines much of its subsequent behavior. The expanding shock from the supernova carries away the outer layers of the progenitor star, but not all of this matter necessarily escapes. Some portion known as fallback material can lose energy through radiation or shocks and spiral back toward the neutron star. The fate of this fallback depends on its mass and angular momentum. If the amount is small, it may simply accumulate onto the surface, altering the chemical composition of the crust and adding only a small increment of mass. If the amount is larger, it may form an accretion disk, transferring angular momentum and affecting the spin period of the neutron star. In extreme cases, fallback accretion can add enough mass to drive the remnant above the maximum mass supported by the nuclear equation of state, leading to delayed collapse into a black hole. The threshold between survival and collapse is not a single fixed number, but depends on the microphysics of dense matter. A stiffer equation of state allows support of masses approaching 3 solar masses, while a softer one collapses at lower mass. Observations of pulsars with measured masses above 2 solar masses already constrain the possibilities, but the exact upper limit is not yet known. Fallback accretion provides one of the natural astrophysical processes that probe this boundary, as it can tip a marginally stable proto-neutron star into collapse minutes to hours after the initial explosion. The observational consequences of fallback include changes in the light curve of the supernova, as accretion releases additional energy and the potential for late-time outflows. Fallback may also bury the magnetic field under newly accreted material, reducing the observable field strength in young neutron stars. Over time, the field may diffuse back out, but the timescales depend on the conductivity of the crust and the amount of accreted matter. Thus, fallback influences both the early and long-term evolution of the neutron star. The ejected material that escapes carries the fingerprints of nucleosynthesis. Explosive burning triggered by the passage of the shock wave produces isotopes such as nickel, 56, cobalt and iron. Radioactive decay of these isotopes powers the light curve for weeks to months. The distribution of heavy elements in the ejector depends on the hydrodynamic instabilities that occurred during the explosion. Clumping and mixing bring inner layers to outer regions, altering the observed spectra, remnants such as the Crab Nebula and Cassiopeia. Show knots of oxygen, silicon and iron, confirming that mixing and asymmetry were significant. The asymmetry of the explosion also affects the motion of the neutron star itself. Conservation of momentum requires that if the ejecta are expelled preferentially in one direction, the neutron star receives a recoil in the opposite direction. This natal kick imparts velocities of hundreds of kilometers per second. Many pulsars are observed to be moving rapidly through space displaced far from their birth sites. The mechanism of the kick is still debated, with possibilities including hydrodynamic asymmetries in the ejecta and anisotropic neutrino emission. Regardless of the precise cause, the large velocities confirm that supernovae are not perfectly symmetric events. As the expanding remnant evolves, it sweeps up interstellar gas and forms a supernova remnant visible for thousands of years. The structure of the remnant depends on the energy of the explosion, the mass and distribution of the ejecta, and the properties of the surrounding medium. X-ray observations reveal shock-heated gas, while radio observations show synchrotron emission from relativistic electrons accelerated at the shock front. These emissions provide diagnostics of the explosion energy, the mass of ejecta, and the environment. They also reveal the continuing presence of the neutron star at the center, sometimes visible as a pulsar wind nebula, powered by the rotation of the neutron star. The neutron star itself continues to cool and spin down. The cooling is dominated by neutrino emission in the first 100,000 years, then by photon emission from the surface. The spin down is dominated by magnetic dipole radiation and winds. The combination of these processes defines the observable properties. Young neutron stars are visible as pulsars or magnetars, while older ones may fade from view as their rotation slows and their emission decreases. The thermal radiation from the surface may still be detectable in X-rays, providing information about the cooling curve. Fullback accretion, if it occurs, can produce distinctive signatures in the early life of the neutron star. The interaction of the accretion disk with the magnetic field can produce X-ray emission. The transfer of angular momentum can alter the spin, either speeding it up or slowing it down depending on the geometry. Over long times, the burial and re-emergence of the magnetic field can alter the appearance of the neutron star as a pulsar, possibly explaining some of the diversity observed in young pulsars. The competition between fullback magnetic field evolution and spin down highlights how sensitive the final outcome is to the details of the progenitor star and the explosion. Two stars of similar initial mass may leave behind remnants with very different properties, depending on small differences in metallicity rotation or envelope mass. This diversity explains why neutron stars observed in the galaxy show such a wide range of masses, spin periods, and magnetic field strengths. The early minutes and hours after collapse are therefore critical, not only for the explosion, but also for the long-term fate of the neutron star. The processes of neutrino emission, shock, revival, fallback, accretion, field amplification, and spin determination all occur in this window. Once complete, the neutron star enters a longer era of gradual cooling and spin down, but the initial conditions established in those early times set the trajectory. The study of fallback accretion also connects neutron star physics to black hole formation. Some massive stars collapse directly into black holes without a visible supernova, while others explode weakly and then collapse after fallback. Identifying which pathway occurs for a given progenitor remains a challenge. Observations of failed supernova where a star simply vanishes from view suggest that direct collapse is real. The role of fallback in these events is an active subject of research, with simulations exploring how much mass can be added and how the transition to black hole occurs. In every case, the interplay of dense matter physics, neutrino transport, hydrodynamic instabilities, and accretion determines the final state. The neutron star that survives, if it does, is the product of these processes, carrying in its mass, spin, and field the record of its violent birth. The aftermath of a core collapse supernova reveals itself across many wavelengths and timescales, providing evidence of both the explosion and the compact remnant. The expanding debris cloud, composed of shock-heated gas and freshly synthesized heavy elements, forms what is known as a supernova remnant. As the ejecta move outward at thousands of kilometers per second, they sweep up interstellar gas, generating a forward shock that heats the surrounding medium to millions of degrees. Behind this front, a reverse shock moves inward through the ejecta, heating them as well. The result is an X-ray bright remnant with complex structure. Filaments and knots trace regions where instabilities mixed elements, while synchrotron radiation from relativistic electrons reveals strong magnetic fields at the shocks. Observations of remnants such as Cassiopeia A show iron-rich clumps at high velocity, confirming that asymmetries in the explosion transported inner layers to outer regions. At the center of some remnants lies the compact neutron star, visible as a pulsar or as a pulsar wind nebula. In the Crab Nebula, the pulsar emits beams of radiation observed across the spectrum from radio to gamma rays, while also driving a wind of relativistic particles that fills the nebula with synchrotron emission. This nebula glows brightly because the pulsar injects rotational energy into its surroundings. Other remnants show compact X-ray sources without pulsations, which may be cooling neutron stars radiating thermally from their hot surfaces. Some young remnants contain magnetars recognized by their bursts of high-energy radiation. The variety of central objects reflects the diversity of conditions during formation, including magnetic field strength spin and fallback. The supernova light curve itself carries information about the explosion. The initial peak arises from shock breakout and the diffusion of energy from the outer layers. Later luminosity is powered by radioactive decay, particularly of nickel-56 to cobalt and then iron. The amount of nickel synthesized determines the brightness of the supernova weeks after explosion. Measuring the light curve and spectra therefore constrains the nucleosynthesis and the dynamics of the explosion. For example, the unusually low nickel yield of some supernovae suggests weak explosions with significant fallback, while high yields indicate more energetic events. Spectroscopy of the ejecta reveals the distribution of elements. Lines of oxygen, silicon, calcium, and iron appear as the material expands and cools. The velocities inferred from line widths provide information about the kinetic energy of the explosion. Polarization measurements show that many supernovae are not spherically symmetric, but exhibit large-scale asymmetries. These observations align with the theoretical picture of instabilities in the stalled shock and neutrino-driven convection shaping the explosion. Over centuries, the expanding remnant cools and mixes with the interstellar medium. Heavy elements produced in the explosion are dispersed, enriching the galaxy with the raw material for future stars and planets. Elements such as carbon, oxygen, silicon, and iron, essential for rocky planets and for life, are distributed in this way. Each neutron star therefore marks not only the endpoint of a stellar life, but also a contribution to the galactic cycle of matter. The connection between supernovae and chemical enrichment is supported by the observed abundances of elements in old stars and in the interstellar medium which match the yields, predicted by models of massive star evolution and supernova nucleosynthesis. Supernova remnants also accelerate cosmic rays. Shocks in the expanding ejecta provide natural sites for diffusive shock acceleration, producing particles that reach energies up to at least 1 pt-electron volt. Radio and X-ray synchrotron emission confirm the presence of electrons accelerated to relativistic speeds, while gamma-ray observations reveal hadronic interactions. Cosmic rays from supernova remnants are a significant component of the high-energy particles that fill the galaxy and strike Earth. Thus, the explosion that forms a neutron star also seeds the galaxy with cosmic radiation. The study of supernova remnants links directly to the properties of the compact remnant. For example, the distribution of ejecta and the momentum of the neutron star are tied through conservation of momentum. A neutron star observed with a high velocity indicates strong asymmetry in the ejecta. The morphology of the remnant can sometimes be used to trace back the motion of the neutron star to the explosion center. Such studies combine observations across radio-optical X-ray and gamma-ray bands with theoretical models of hydrodynamics and nucleosynthesis. The neutrinos emitted during the first seconds of the collapse carry direct information about the protoneutron star. Future detections of thousands of neutrinos from a galactic supernova would provide precise timing and energy spectra, allowing astrophysicists to test models of neutrino transport matter at nuclear densities and shock revival. Coupled with gravitational wave detections from the same event, these signals would offer a complete picture of the core collapse. Gravitational waves trace fluid motions and asymmetries, neutrinos trace weak interactions and energy transport, and electromagnetic radiation traces the explosion and its aftermath. Together they form a multi-messenger view of the birth of a neutron star. Over longer timescales, the neutron star continues to evolve. Its rotation slows its magnetic field decays and its surface cools. Pulsars fade from the radio sky as their rotation slows below the threshold for pair production in their magnetospheres. Magnetars release their magnetic energy in bursts until their fields decay. Cooling neutron stars emit X-rays for hundreds of thousands of years, then fade into invisibility. Yet even when unseen, they persist as compact remnants moving through the galaxy, silent witnesses to their violent origins. The diversity of neutron stars observed today reflects the range of initial conditions at their birth. Some become ordinary pulsars with moderate fields and spin periods. Some become magnetars with ultra-strong fields. Some are spun up in binaries to become millisecond pulsars. Some collapse into black holes through fallback or later accretion. Each pathway begins with the same fundamental process: the collapse of an iron core, the formation of a proto-neutron star, the emission of neutrinos, and the revival of the shock. Supernova remnants, pulsars, magnetars, and millisecond pulsars are therefore all connected as stages and outcomes of the same physical chain. The mechanisms that govern each stage are complex, involving quantum mechanics, nuclear physics, general relativity, and plasma dynamics. Yet the broad sequence is clear. A massive star ends its life when ion fusion can no longer supply pressure support. The core collapses, rebounds, and forms a proto-neutron star. Neutrinos carry away the binding energy, heating the region behind the shock and driving an explosion. The remnant cools and contracts into a neutron star, which then evolves over millions or billions of years depending on its environment. The observations available across these timescales confirm the theoretical picture while also highlighting uncertainties. Neutrino detections confirm the energy release. X-ray spectra confirm the presence of heavy elements and mixing. Pulsar observations confirm rapid rotation and strong magnetic fields. Cooling curves confirm the influence of superfluidity, yet open questions remain about the exact mechanism of shock revival, the composition of matter at several times nuclear density, the origin of the strongest magnetic fields, and the conditions that separate neutron star survival from black hole formation. The neutron star that survives a supernova is thus both a product and a probe of physics at extremes. It embodies the outcome of gravitational collapse, the properties of dense matter, and the interplay of nuclear weak and electromagnetic forces. By studying neutron stars and their remnants, astrophysicists uncover the processes that govern the most energetic stellar deaths and the birth of compact objects that endure across cosmic time.